let's let f of x be 2x plus 1. And let's go ahead and let our interval be same one from last week, the interval from 0 to 10. So I'm using closed interval notation there to emphasize what the interval is. I'd like to set up, say a right-hand sum. Let's see if we can do a right-hand sum by hand. Okay. So what does that mean? I need to identify, last week we used t sub to 0, t sub 1, t sub 2, t sub 3, etc. Remember that? Here, let's use x sub 0, x sub 1, x sub 2, since we have x for the variable. Let's first let delta x instead of delta t be b minus a over n. What does that equal? That's equal to the length of the interval, right? If a is less than b, which is what I am assuming here, a is less than b, b minus a is going to be the length of the interval. In this case, it's 10 minus 0, it's 10. And n is the number of rectangles that I'm going to use to approximate the area. You could also say it's the number of subintervals of the bigger interval. You got this big interval from a to b, 0 to 10 here. I'm trying to break it up into a bunch of pieces, maybe 10 pieces, maybe 100 pieces, maybe 1,000. All of the same length, just to keep things simple. In that case, if I do 1,000 pieces, it would be 10 minus 0 over 1,000. 10 over 1,000 is 1 over 100, 0.01 would be the length of each subinterval. That's going to be the base of each rectangle. The heights are going to be bigger in general. But I'm trying to do this abstractly, so I'm not going to specify what n is here, but I will go ahead and plug in a and b. So this becomes 10 over n for this example. I'm going to let, okay, let's do it piece by piece first, then we'll write down the general formula. I'm going to let x sub 0 be the left endpoint a, that's 0. Let x sub 1 be x sub 0 plus delta x. So in general, that's a plus b minus a over n, which for our example is 0 plus 10 over n is 10 over n. When n is, yeah, that's right, 10 over n. Again, not saying what n is. I'd like to keep n unspecified. I'd like to keep n as a variable because that's what I'm going to let go to infinity in the end. x2 is going to be x1 plus delta x. But x1 is x0 plus delta x. So that's really x0 plus 2 times delta x in general. For our example, that's 0 plus 2 times 10 over n, 20 over n if you like. x3 is going to be x2 plus delta x. I just keep moving to the right by delta x units. But x2 is x0 plus 2 times delta x. So this simplifies to x0 plus 3 times delta x in general. For our example, that's 0 plus 3 times 10 over n, 30 over n. We see a pattern here. In general, x sub I, where I could be 0 or 1 or 2 or 3 or 4, etc. In the end, that's going to be x0 plus I times delta x. And for our example, that's going to be I times 10 over n, or 10I over n. And if you keep going, how far do you go? The last subscript would be an n. n, xn, what's n, xn? Let me replace x0 with a plus n times delta x. I can replace x0 with a because x0 does equal a. I said that at the beginning. In the general case, I'm out of paper here, so I'm going to put this up here. In the general case, this equals a plus n times b minus a over n. The n's cancel, giving you a plus b minus a. The a's cancel, leaving you with b. Xn, even in the general case, equals the right endpoint, b. For us, that's 10. Okay, yeah, that's the nth, the right endpoint of the nth subinterval, and there are n subintervals. It's got to be the very far right endpoint, b, and it does work out to equal b. What now is a right-hand sum say? Right-hand sum, or say right of n, meaning a right-hand sum with n intervals. I'm saying of n because I actually mean this to be a function of n. This function's name is right. There's also a left. If you write it without a summation sign, what's the right endpoint of the very first interval? The first subinterval goes from x0 to x1. The right endpoint's x1. F of x1, that's the height of the rectangle times delta x. The next rectangle has a height f of x2 times delta x. I'm writing down a general formula in this case, but we will simplify it for our example. That's a right-hand sum with n subintervals. You should start feeling comfortable with summation notation as well. Capital sigma, summation notation, means sum. I goes from 1 to n. It's understood I starts at 1, and then I becomes 2, and then I becomes 3, and then 4, etc. through n. You're adding up products f of xi times delta x. It's understood that these two things are equal to each other. This is just shorthand notation for that. Just a little quicker to write. Summation notation is hard for people to get used to typically. It's something to work at. It is convenient for programming Mathematica, we will see with summation notation. What does this equal for our example? For our example, what is xi? It's 10i over n, right there. 10i over n. What is delta x? It's b minus a over n, which we found to be 10 over n, right there. There's delta x. Is it possible to simplify this for our particular function f of x equals 2x plus 1? Yes, it is. This is the hardest part right now. Okay, what do we need to do? We need to use our function's formula, 2x plus 1. I've got f of 10i over n. In the formula 2x plus 1, I need to replace the x with 10i over n. 2 times 10i over n plus 1. That gets multiplied by delta x, which is 10 over n. Okay, doesn't look like this is going to be so easy, but let's just keep going and see what happens. This simplifies to 20i over n, and then I can distribute the 10 over n through these parentheses here. 20i over n times 10 over n becomes 200i over n squared. And then 1 times 10 over n is just 10 over n. Okay. Now what? Let me just do a little side calculation here to illustrate what this means. If I've got a summation, you don't need to write this down unless you want to. It's a side calculation. If I've got a general summation, say like this, a summation of a summation, adding up terms of the form AI plus BI, where first I is 1, then I is 2, then I is 3. This means A1 plus B1, then plus A2 plus B2, then plus A3 plus B3, etc. The last thing that would be added would be AN plus BN. Because of the commutative property of addition, I'm adding a bunch of things here, and the associative property. Doesn't matter where I put the parentheses. In fact, I can get rid of all those parentheses. I can rearrange the A's and the B's. I can group all the A's together and all the B's together. And I will put another set of parentheses in here for emphasis that I'm grouping these things together. That's essentially just the associative property for addition as well as the commutative property for addition. You might say the commutative property being the more important of the two. The fact that I can switch the A's and the B's around. And the first thing I have there is the sum of the A's. And the second thing I have here is the sum of the B's. So because of those properties, I have just derived effectively a property of summations that these two things are equal. Effectively, it's almost like you are distributing the summation sign through the parentheses, even though that's not literally what you're doing. Right? The summation sign is not a number. It's just a symbol. It means add. So I'm not actually multiplying the summation times this, and I'm not literally using the distributive property to go from here to here. It just kind of feels that way. It is based on the associative and commutative properties of addition. Let me do that here, with this thing being like the AI and that thing being like the BI. So I get the sum of two summations. Like this. Each of those feels a little simpler, perhaps, than the other one, than this one. But it still probably feels kind of difficult. What should I do now? Right, well, I'm teaching you what to do. Look at the summation. What's the variable? Is I the variable, N the variable, or both? Well, there is a sense in that both of them are variables. But as far as the summation is concerned, only I is a variable, because that's the only thing varying. The N is not varying here. I am thinking of, in all these calculations, I'm imagining N to be fixed. Now, after I finish the calculation, I will let N go to infinity, so it won't be fixed in the end. But when doing the calculation, I am thinking of N as fixed. I is the variable. I is what's changing. Anything that is a constant that doesn't involve an I as a multiple here can be factored out. That's really a property of summations as well. If I've got a summation, I goes from 1 to n of a constant times AI. What does that mean? It means C times A1 plus C times A2, etc., through C times AN. Because of the distributive property, I can factor the C out like this. And then I can replace what's in parentheses with a summation like that. That's another property of summations, that this equals that. That's what I'm about to use. Back up here, treat the 200 over n squared like it's the C. Bring it in front of the summation. Like this. Don't worry about the fact that you don't know what n is. with respect to the summation, it's still a constant. You might be wondering, do I really have to do this on the test? With help, if I put it on the test. I put problems like this on tests before with some help. There's one more big step here we're about to do where we're going to need a lot of help, actually. What about this one? Is the 10 over n a constant? Can it be brought in front? Sure. Should I bring it in front? Well, you don't really have to. Maybe I will just for emphasis. I can bring the 10 over n in front of the summation, but what am I left with if I do? What goes here? 0? No. 1. I've got a bunch of 10 over n's being added together. N 10 over n's, in fact. Each can be factored out and get a 10 over n in front with a bunch of 1s, n 1s. Yeah, I'm adding up n 1s. Hey, yeah, that's just n. If I add up n 1s, I get n, right? And then if I multiply that by 10 over n, 10 over n times n, the n's cancel, giving me 10. Yeah, I was adding up n 10 over n's to get 10n over n, 10. That's nice and simple. Oh, I still got this, though. What do I do about that? Anybody happen to know what I should do about this? Just wondering if anybody's... What am I really doing there? I'm adding up the first n numbers. Like if n is 5, I'm doing 1 plus 2 plus 3 plus 4 plus 5. Well, you're most familiar with n is 3. 1 plus 2 plus 3? No. N is 4. Plus 4 is like pins in bowling, right? You got your pins, 10 pins set up, 1 plus 2 plus 3 plus 4 of them, 10 pins. They're like in a triangle. These summations define what are called triangular numbers. You've heard of square numbers. If you've never heard of triangular numbers, this is the first time you're hearing of triangular numbers. Because they form triangles. If n is 1, it's a triangle with 1 dot. If n is 2, it's a triangle with 1 plus 2, 3 dots. If n is 3, 1 plus 2 plus 3 dots is 6 dots total. If n is 4, that's like bowling. 1 plus 2 plus 3 plus 4, 10 dots for 10 bowling pins. I was having trouble remembering what n was for bowling for a minute there. If n is 5, you've got another 5 dots, bringing you to a total of 15 dots. N is 6, got 6 more, bringing you to 21. The numbers 1, 3, 6, 10, 15, 21, etc. These are called triangular numbers. Whereas, square numbers are perfect squares. 1, 4, 9, 16, 25, 36, right? Those are squares. Square numbers, they can be put into squares. That's why they're called square numbers, in fact, because you can make the dots into squares. Or if you prefer, you can have squares that are actual squares with these with side lengths equal to square roots of these things, and then these numbers are the areas. With triangular numbers, it's best not to think of them in terms of areas, unless you do some tricky geometry, but instead of number of dots. You might wonder, is there a shorthand formula for these triangular numbers? The answer is, there is. What is it? Mathematica, please tell me. Mathematica, summation, I goes from 1 to n. By the way, to get to these different boxes, I'm just tabbing. I. This represents adding up the first positive whole numbers and n positive whole numbers. 1 plus 2 plus 3 plus 4, etc. through plus n. What does it equal? Do you know Mathematica? You do. 1/2 times n plus 1. Or a more typical way I write that by hand is n times n plus 1 over 2. Does it work? Try it. When I is 4, so we get the bowling pins. When n is 4, this gives 4 times 5 over 2. 20 over 2 is 10. When n is 5, 5 times 6 over 2. 30 over 2 is 15. Yeah, it's the next triangular number, 15. When n is 6, 6 times 7, 42 over 2 is 21. It's working. Is that a proof? No, but I hope it feels good enough. To prove it, you can use mathematical induction. In fact, if you take discrete math, it'll probably be an exercise for you to prove that these things are equal with induction. But we won't do that in calculus. Have you heard of mathematical induction? Maybe, maybe not. Oh, mathematical induction. So much fun. All right. Like, wait a minute, I thought induction is only in science. There's mathematical induction that's in math. It's not the same thing as scientific induction. All right, so where are we? What do we have here? We got, let's write it out here. What we've just figured out is evidently that right of n equals 200 over n squared times n plus 1 over 2 plus 10. Okay. 1 n can cancel. This 2 can cancel with the 200. I guess leaving me 100 times n plus 1 over n. Only one of those n's canceled there. Plus 10. What's the limit of this as n goes to infinity? Does it exist? If it does exist, that should be the answer for the area under the curve. The integral from 0 to 10 of 2x plus 1 dx should be, if I have not made a mistake, the limit as n goes to infinity of this thing. What's the limit of that as n goes to infinity? It's a rational function of n. In fact, this part can be thought of as 100n plus 100 over n, which we know from chapter 1 goes to the ratio of the coefficients of the highest powers when the degrees are the same, 100 over 1, 100 as n goes to infinity. Could I also use L'Hopital's rule there? That might feel a little funny since n is a discrete variable instead of a continuous variable, but it does give the right answer, 100. So it looks like the limit is, in the end, then 100 plus 10, 110. Is that right? Trying to find the area under this trapezoid. Oh, we did this last week, didn't we? Height there is 1. Height here was 21. Right, this graph is y equals 2x plus 1. Height when x is 0 is 1. Height when x is 10 is 2 times 10 plus 1, 21. The area here is the base 10 times the average of the heights. 10 times 22 over 2 is 11. 110. Same answer. Oh, why didn't we just do that? Well, we wanted to see that the limit gives us the right answer. That's why. And once we go to t squared or x squared, once we go to x squared, we can't do this anymore because it's not a simple geometric object anymore. We have to do the limit.